Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors 8-3 lesson on infinite geometric series. In this one, we will be determining if an infinite geometric series converges or diverges, and if it does converge, we will be finding the sum of a geometric series. To start this lesson off, now that you've had some experience using sigma notation the long way, guess what? There is a way to do it on your calculator. If you go to Alpha Window 2 or Math 0, you can pull up a sigma function that lets you enter all this stuff in. So pause the video, pull up that function, and see what this comes out to on the calculator. So here I am on my calculator, and if I'm being honest, Math 0 is less button pushes than the other way. So let's enter all that in. Now it's already going to be default in alpha mode, so I'm just going to do n right here, and then we have a lower limit of 0, an upper limit of 5, and a sum end of 2 exponent, and then we have to use the same letter, so we're going to have to do alpha n for that. And you could use x if you wanted to, if you don't feel like doing the alpha, but I like n in there. So pressing enter, we've got 63 that comes out to, and just to double check to make sure we did it right, if we expand this, we're basically taking all the powers of 2 from 2 to the 0 to 2 to the 5th, so that's 1, 2, 4, 8, 16, and 32 that we're all adding together, and that will come out to 63 if you take the time to add it. So that's nice. So why did I show you this now? Well, you need to know what sigma does in its own right. But the other reason I want you to have this is I've got a second warm-up for you. This one's even cooler. For this warm-up, I'm going to have you create 2 functions using sigma. So the way you're going to set up these functions is you're actually going to make like the upper limit, the input on these functions. So we're going to do y1 equals sigma from 1 to x of 2 to the n, and then in y2 you're going to do pretty much the same stuff, but you're going to have 0.5 instead of 2 for your common ratio for this geometric series here. So pause the video, follow these directions, check out the table, and see what happens as you increase this upper limit. So if you want, you can also follow along in my calculator. Here's what I set up in my y equals, and now I'm going to go to second table, and I'm starting with a table initial value of 0, and then we're going up by 1s. So here's the first one that has the 2 to the n. Here's the second one that has the 0.5 to the n. And as we increase there, we see that both of these sums are getting bigger and bigger, which we would expect because these are all positive numbers that are getting added together, and bigger and bigger. And as we keep going, we see that although this second one is getting bigger, it's not getting bigger as fast as the first one. The first one just keeps growing and growing. I mean, here we're up to 4,000 and change. Over here, we're almost at 1, but we're not even quite there yet. And as we keep going further and further and further and further, at some point, this just gets rounded off to 1, and we keep seeing 1s for a long time. Meanwhile, over on this 2 to the n, like we're going to 10 to the 8th power. Just crazy orders of growth over here. So this is kind of interesting, right? With one series, it just kind of seems to keep growing without bound. The other series, it doesn't seem to be able to get past 1. So although these are, I mean, what would happen if these were both going to infinity? This first series, I think we can pretty clearly say, is just going to keep growing. But how about this second series? I mean, does it just stop at 1? Is it possible for an infinite geometric series to have a finite sum? Before we address the question of an infinite series with a finite sum, let's get some definitions out there. We would say a series converges if it approaches a single finite number. So we're basically asking, can an infinite series converge? And we would say a series diverges if it either grows without bound, so to infinity, or if it keeps oscillating back and forth between a few numbers. So if you have a common ratio that is 1 or bigger than 1 for a geometric series, an R value bigger than 1 or 1, that series is going to have to diverge. If you think about this, a common ratio bigger than 1, you're adding numbers that keep getting bigger and bigger. So obviously those are just going to add up to infinity if that's a thing, if you keep adding more and more of them. If you have a common ratio of exactly 1, then you're just adding the same number over and over again. And again, that's just going to go to infinity if you have an infinite number of those. Now, the more interesting case is if you have a common ratio of less than 1. So this is a situation where you're adding numbers that are getting smaller and smaller and smaller. In that case, it can be shown that an infinite series is going to converge with a common ratio less than 1. Here's why that is. So as n approaches infinity in the following formula here, so this is our geometric series sum formula, as n approaches infinity with a common ratio that's less than 1, what's happening with this common ratio less than 1 is that your number is getting smaller and smaller and smaller the more r's you multiply together. And if you have an infinite number of these r's making each other smaller and smaller and smaller, eventually you can consider this r to the n term to just be effectively 0. And if that's the case, you've just got a times 1 over 1 minus r, which gives us the sum of an infinite geometric series formula, a1 over 1 minus r. Now this is kind of a cute formula because to add up an infinite number of terms, it's actually nicer looking than when you have a finite number. But this is our infinite sum formula that we'll be using now. At this point, we're going to try to figure out the sums of a few infinite series. But before you do that, you first want to figure out if each of these series converges or diverges. Because if you have a diverging series, there's no point in trying to find out what it converges to, right? So let's try this first one out. Pause the video and see if you can figure out if this converges or diverges. All right, so if you're looking at convergence, hopefully you took a look at the r value, the common ratio, which on this one is negative 1/3. So since that r value is less than 1, and we're just talking about the absolute value of this now being less than 1, that means that this series is going to converge. Because, I mean, we've proven here with this r value that these terms keep getting closer and closer to 0. Okay, so pause the video and see if you can actually find the sum now. So to find that infinite sum, we have to do a1 over 1 minus r. That's our nice little infinite sum formula. So our a1, that's going to be 1, this first term. And then we're subtracting negative 1/3 down there for our r value. 1 plus 1/3 then, that's really like having 3/3 plus 1/3, or so 4/3. And if we have that in the denominator, we just have to multiply by the reciprocal. So that ends up being 3/4 for that sum. All right, pause the video and give this next one a shot. So again, hopefully you looked at the r value, which in this case we've got 20 over 5, which is an r value of 4. The absolute value of 4 is greater than or equal to 1. So that's the case where we have a diverging series, which is to say this does not have a finite sum. We're going to do a couple more examples with infinite geometric series, this time using sigma form. And you'll notice on both of these we have upper limits of summation that are infinity. So pause the video and see if you can figure out convergence, divergence, and the sum, if possible, for this first one. All right, so I'm going to go through and get the a1 and the r right off the bat here. So the first term can be a little bit tricky with these sigma forms. To get a1, you have to plug in your lower limit of summation into n. So this is going to be 6/5 times 1/4 to the 0. That means that we're really just doing 6/5 times 1, which is just 6/5. Now for the r, that's going to be whatever we're multiplying by over and over again. That's going to be the 1/4 that's being raised to this variable exponent. And since 1/4 absolute value is less than 1, that means that we have a converging series here. So let's go ahead and find the sum. That's going to be a1, so 6/5 over 1 minus 1/4. So this is going to be 6/5 over 3/4. And then doing same change flip here, we've got 6/5 times 4/3. That's 24 over 15, which we can reduce to 8 over 5. All right, let's go ahead and do this next one now. We'll start this next one together because this can be a little bit tricky in the beginning. So for this one, whenever you have exponential functions in both the numerator and the denominator, both exponential functions, you can try splitting up the bases and see if you can get an a1 and r out of that. So here's what I mean by that. Like this 6 to the n plus 1, we can split this up into 6 times 6 to the n. And now that we've done that, I can just kind of separate this off to be like 1 over 6, and then I've got 5 to the n over 6 to the n. Now this 5 to the n over 6 to the n, we could also call that 5 over 6 all raised to the n power. So this is what I'm talking about splitting up bases and getting an exponential term out of this. Now that we see this, pause the video and see if you can do the rest of the problem. All right, so our a1 out of this, if we raise this to the first limit of 0, that's going to be 1/6. And then the r value, that's this 5/6 that keeps getting multiplied by itself over and over again. That is also absolute value less than 1. So we have another converging series. So this then is going to be our a1 value of 1/6. And let me just make that an a1 there. So a1 value of 1/6 over 1 minus 5/6. So this is just 1/6 over 1/6. Well, that's just going to be 1. Just to mix things up, we're going to do this one last problem. This time they want us to find the common ratio of an infinite series, geometric series, with a sum of 12 and a first term of 5. Pause the video and see if you can reason out how to do this one. All right, so I'll start by writing my formula. Again, S equals A1 over 1 minus R, which we can use because it's an infinite geometric series. And this time around, we're not looking for the sum. We've already got that. They told us it was 12. We're trying to find the common ratio, R. We do know the first term, A1 is 5, so let's plug in the sum and the A1 that they gave us and solve for R. So we can write 12 equals 5 over 1 minus R. And then if we multiply both sides by 1 minus R, that's 12 minus 12R. Subtracting 12 over here, that's going to be -7. And then dividing by -12, we have a common ratio of 7/12. So that's it for this one. Although some of the problems involve infinite things, the lesson itself is finite. Till next time, Mr. Sutton signing off.